Greetings and welcome back. In this section, we have question 6 from the Doppler effect, the question on Doppler effect. This is coming from the DBE 2022 past exam question in physics, that is paper 1. The question goes as follows. A car moves at a constant speed of 10 meters per second towards a stationary sound source. The sound source emits sound waves of frequency 880 Hertz. So we are given some data as usual, as is always the case in physics. Speed 10 meters per second, frequency 880. Okay, and then it goes on to say that a sound detector A is attached to the sound, and another sound detector B is attached to the sound source. Detector B detects the sound waves reflected from the car. The speed of sound in A is 340 meters per second. So we are given the information here. And then 6.1 is to state the Doppler effect in words. There are many ways that you can state it. So my favorite one is just to say that the Doppler effect is the apparent change in the frequency, some say pitch, okay, frequency detected by a listener when different texts, you find that they will put it in different ways, so you can find your own way that is you can understand much better. So that is the Doppler effect, the apparent change in the frequency detected by a listener when the listener and the sound source are moving relative to each other. So that's how you state it. Then 6.2 is to calculate the wavelength of a sound waves emitted by the source. So we are told that B is emitting a sound, and that sound is a frequency of 880. So we are required to calculate the wavelength. The wavelength, the symbol for wavelength is lambda. So we are basically given lambda here, and we are given frequency there, which is F, and we are given V, which is the speed of that sound in A. So which means we are going to use the formula that combines these three variables, which is V is equal to F lambda. Okay, translate this one into our V will be 340, substituting there, F is 880 times lambda, and then that leaves us with the lambda being equal to 340 over 880. Okay, and the answer is therefore our lambda will be equal to that. Okay, so let's work it out. We'll get 340 over 880. We get 17 over 44, which we can write in decimal format 0.3863. So that is 0.3863. That is in meters. So that is the wavelength of that particular sound source. 6.3 is to calculate the frequency of the sound waves detected by detector A. Okay, 6.3. Now, detector A, remember, we are given that it is acting as our listener. So basically, we are calculating the frequency detected by the listener because it is approaching, it is detecting the sound from B. So B is emitting sound and A is detecting that. So we are now going to use the Doppler equation. The Doppler equation, which states that FL, the frequency detected by the listener, is equal to V plus or minus VL over V plus or minus Vs times Fs, okay, which is the frequency of the source. So in this case, there are two formulae in this one. So we know that there's one particular formula that we use when the objects are moving towards each other. That's why towards is highlighted there in capital letters. So if they are moving towards each other, we use a plus sign on top. Okay, we use a plus sign on top and a negative sign at the bottom. So this will be V plus VL over V minus Vs multiplied by Fs. I've seen most students, they rather confuse this one. So take note that if you are applying this formula, okay, there is always opposite signs, okay, on the numerator and the denominator. If you use the plus on the numerator, then your denominator will have a negative. If you use a negative on top, then your denominator will have a plus. That's one thing. So secondly is to know that when the objects are moving towards each other, so we expect the frequency to increase, so the numerator should be bigger, so we use a plus sign. There must be a plus sign here, okay? So once you use a plus sign, then the denominator will have a negative sign. So we are going to apply this formula and substitute our values. So eventually have V represent the speed of sound, which is given there, which is 340 added to V is the speed of the listener. Okay, so the listener is our car because it is the one that is detecting the sound. So we are told it's moving at a speed of 10 meters. So add 10, divide that by V, subtract Vs. Vs is the velocity of the source or the sender. Our source is the sound source, which is emitting the sound. So it is stationary here, it's not moving. Okay, so we have to say our Vs is 0. Okay, anyway, by the way, our V here is 340. So let us substitute there. That will be 340. Okay, and then all that we multiply by the frequency that is emitted by the source. Our frequency emitted is 880, so we multiply that by 880. Okay, the answer therefore, our FL, frequency detected by the listener, which is detector A, is going to be that. Let's enter it into our calculator. Okay, we have fraction first. 340 plus 10, I will enter that as 350, 350 over 340, okay, and that will multiply the 880, so 880. The answer will give us, in decimals, 905.88. So that will be 905.88 Hertz. Okay, so that is the frequency detected by A. Let's come to the last part of this section. Okay, the last part of this section is asking us to sketch the graph below, showing the frequency recorded by detector A, and then redraw the graph above for detector A in your answer book. On the same set of axes, sketch the graph of the frequency recorded by detector B. Label this graph as B. So what we know here is detector A is detecting a sound of 905. Okay, it is detecting a sound of 905.88 Hertz. So that is the value of A there. Now we are told here that detector B is detecting the sound waves that are reflected from the car A. Okay, so car A, it is receiving a frequency of 905.88. Now, which means now when the waves are reflected, which means they are thrown back, so that one is now acting as a new source of sound. Okay, so basically we are now saying that the car is emitting a sound because the same frequency that is detected here, it is now bouncing back. So we treat that as an FS. Okay, frequency emitted by the detector or by the car. So now we almost have got a double Doppler effect here. So since the car is moving towards B and it is emitting a frequency of 900, or the frequency is being reflected, so it means the fact that they are moving towards each other, so B is going to receive a higher, is to record a higher frequency than that which is emitted, but they are moving towards each other. So what we have here is fact that we have got B, that is the graph for B, the frequency for B is going to be a little higher. Of course, we don't know that. We could calculate it. So it will be a little higher than the frequency of A because they are approaching each other. So coming to drawing that, the question requires us to do is to draw the frequencies here. Okay. So we have over here okay, so that is our frequency, and let's just call it F in hertz. Okay, and this one is our time in seconds. So what we are going to have is one, we will have A, as it is requiring us to redraw there. So A is this one, okay, and our B is also going to have a little bit higher. We'll draw a higher line there. Okay, so as stated, this is our A and that will be our B. Okay, the bottom line is 1, they must be parallel to each other. Okay, because why they are parallel is that it is the same frequency, that is, the frequency is not changing, it's just higher but it remains constant. Okay, it will change down if possibly when the car passes the detector, the listener here, the detector B. Okay, so we will have a sharp drop in the frequency, but since it is now in the approaching phase, it's all same frequency. Okay, so